Okay, so we've had 3 lectures up to now on computability according to Turing machines. Then we have the Turing machine model of computation. And one of the things we did last week was we used that to define what it means for a partial function on natural numbers to be computable. So last week, find we can think of it like this. For any k, we defined the set of, set of partial functions, as we said what it means for a partial function to be computable. So in doing so, we implicitly defined for any k a set of partial functions that is computable. Partial functions on the natural numbers. And for this, we used the representation, the binary representation of numbers, but we saw it didn't matter really which representation of numbers we used. We used the representation of k tuples as being separated by commas, as k words separated by commas, and we used Turing machine computability for that. And so we have such a set for any k, so it's really giving us a family of sets. And we'll actually consider this family of sets indexed from 0 upwards. So in the case of k equals 1, we have the unary computable part. Unary means they take a single argument. The unary computable partial functions on the natural numbers, when k is 2, it's the binary. What do we have in the case k equals 0? What are the computable partial functions from natural numbers to the 0 into natural numbers? Yes?
We have the constants.
Okay, and what are the constants?
Natural numbers.
Okay, so we have one constant for every natural number. Do we have anything else? We also have the constantly undefined function. Okay, so there are countably many, but one for each natural number, and also the constantly undefined function. We only have one argument of zero-arity, which you can think of as an empty tuple, but your partial function can still be undefined. Okay, anyway, the point is we're considering computable partial functions of whatever arity we wish. And these are very fundamental in the study of computability, because functions on the natural number functions on the natural numbers are very fundamental mathematical objects, and so we're looking at some very fundamental mathematical object, namely functions, and we're asking when such things are computable. So we call the above family the computable partial functions. When we talk about the computable partial functions without further qualification, we mean the computable partial functions on the natural numbers. If we were needing specific, we would say computable partial functions on natural numbers. And these things are very thoroughly studied in all books on computability theory. It's clearly something of interest whether a function on the natural numbers is computable. In most textbooks, they only consider k from 1 upwards. But Davarin, who's the teaching assistant, strongly prefers me to include the case k equals 0 here, so he's persuaded me to do that. It very slightly simplifies one of the definitions that will appear in this lecture. Okay, so we've got the computable partial functions, and our understanding of them so far comes through the notion of Turing machine. We've used Turing machines to define computability, and from that we've defined the computable partial function. So the main topic today is a completely different understanding of the computable partial functions, which is machine independent. So it's no notion of machine, and it's very mathematically pure in a sense. It's just defined using nice mathematical concepts. So today, a mathematical machine independent view of the computable partial functions going to see is that the computable partial functions coincide with another class of partial functions, which we can define using very nice mathematical notions in the definition, from which it's far from obvious that the two classes coincide. So it's really, I mean, I'll talk more about it later when we see what we're doing. But I think it's a really beautiful result today. So today, we're going to look at this machine-independent view of computable partial functions, and that is, we're going to see that computable partial functions coincide with another class of functions that we can define independently, the computable partial functions, partial function. Coincide what's it called? Partial recursive functions. The partial function, recursive functions actually have an interesting history that slightly predates Turing's work, in that they were considered by Gödel when he did his work on independence theorems in logic, and maybe somebody called Jacques Helbrand had a little bit of input into this too. I just can't quite remember. I haven't looked at the history recently. But anyway, Gödel had considered this notion, but he hadn't thought of considering it as a notion of everything that is computable, all the functions that are computable. He just realized that he had a notion that gave him a lot of useful computable functions on the natural numbers. It was only with Alonzo Church's work on the lambda calculus and Turing's work on Turing machines that then some other definitions of computable partial functions came in, and then Turing proved that all these definitions coincide. And so then it was realized that Gödel's definition was, in a sense, the first definition of good definition of computability. It's just he didn't realize that it was a good definition of everything that was computable, like he made it. Okay, so we're going to look at the partial recursive functions. There are two steps to that. We start off with something called the primitive recursive functions, and then we extend the definition a little bit, and we get something called the partial recursive functions. So let's go to another board, and we'll look at the primitive recursive functions. The primitive recursive functions, so both these classes have nice, elegant mathematical definitions. They're much more elegant in the sense than the notion of Turing machine. It's capturing completely different intuition. But nonetheless, definitions will take quite a lot of board space. So I'm going to first define the primitive recursive functions, and that's probably going to take us pretty much all the rest of the first hour to do that. But nonetheless, bear in mind it's an elegant definition. I mean, it took quite a long time to define Turing machines too. Let's move the camera. Right, so let's define the primitive recursive function by writing. Probably will help to split the board in two. So the definition, primitive recursive functions we're just going to go all out and simply, with a hammer, define a class of partial functions on natural numbers. Actually, in this case, it's going to turn out that they're all total functions. The primitive recursive one. We'll see that later. So, primitive recursive functions, got it written in full out there, so I'll just write prim dot rec dot for the abbreviation. The prim rec functions are smallest collection call it a curly f, but the point of a curly f is just to be used in this definition. Afterwards, we'll just call it a primitive recursive functions. I'm not going to use this symbol later on in lectures when referring to them. So, simply a collection of partial functions for every arity. So again, we'll allow, there's a subset of family consisting of partial, the family indexed by, point there, indexed by arities, again allowing an arity of 0, and for every arity of 0 we have a set of all partial functions, but we're looking at a sub-family. For every k sub-collection, the collection of all partial functions. And again, in most textbooks, k goes from 1 up, but here we're going to have also arity of 0 to slightly simplify the definitions. So smallest collection of partial functions that satisfies some properties. It's a smaller collection that satisfies the following properties, and the properties are called, I'm going to number them, they're numbered 1 to 3. That is, so the smallest collection of partial functions satisfying 1 to 3 alike. So 1, I'm just thinking whether I can fit it onto the board here. Let's try. So 1 is called basic functions. This is addition 1 on this smallest collection. And this is that this collection isn't empty. It contains a few basic functions which we will now specify. So these are, f contains 0 function, which I'm going to use capital Z for. So in textbooks, Z is the 0 function is defined as a unary function on the natural numbers that is the constant function that maps any natural number to 0. Okay, but it very slightly simplifies the definitions to use the feature that we've got here that we're allowing also arity 0 functions to have 0 as a 0 arity function. So this is the 0 function goes from the 0 arity function, doesn't take, it's just the empty tuple as its argument. It's going to write everything as a partial function, even when it's total, because we're talking about families of partial functions, and it's defined by Z of the only argument one has of 0 arity, the empty tuple is 0. Okay. So it contains the 0 function. It says in the notes the 0 function, I won't write it down, it's contains the successor function. This needs to have an argument. But the successor function takes a number n. Got x in the notes, so let's stick to the same thing. What's the successor of x? Who knows what I mean by successor? X plus 1. Definitely English, not mathematics, there. But at least I hope I am. And it also contains the projection functions, and that's for every arity k, which is greater than or equal to 1. So you have a projection and 1 and argument that we can project it on. So that's the arguments from between 1 and k. The function is called u superscript k, so projection from the k tuple, subscript I, the ith projection, which of course, when so this goes from this is a k, a real partial function, but again it's total. Of course, u superscript k I, we give it k tuple of arguments x1 to xk. And this is one place in the notes where I'm counting from 1, not counting from 0. It turns out I'm not very consistent. But anyway, we project on the ith argument and get back x. And the point is that our primitive recursive functions include all these functions. Okay, so we have some functions of every arity, some partial functions of every arity, and so far they're all total. Okay, those are the basic functions. Second condition is that the primitive recursive functions are closed under function composition, or in this case, we've got partial functions a priori, so composition of partial functions. Call that condition composition. And that's if. So how do we compose functions here? If they were unary functions, it's obvious what we mean by composing the functions, but here we have a function from the k tuple of numbers into a single number. So the way of composing is we need a k tuple of functions to compose them. So that means if we have partial function arity k, and we have k different partial functions, some other arity, or could be the same arity, but anyway, let's call that arity L. And the point is what we want to say, we can always, if we've got such data, we can always compose them. But what we want to say is that if this function and these functions are in F, are in the family curly F, that we've defined that we're putting constraints on, but whenever we have some functions in the family, and also the composition of those functions. So if these are in F, can be specified, then so is the composite. So the composite here, we're going to write it using standard kind of composite notation. So we're composing F with on the right, well, we kind of compose with a tuple of functions. So I'm going to write it like this, G1 to GK. So this goes from N to the L, the arity, which is the arity of each of the G's, to N. And it's defined by, if we apply F of G1, GK to an L tuple, X1, XL, then we get back f of g1 of x1 to xl. So these L arguments are just shared by all the G functions. So it's really, think about it, it's a natural notion of composition for these kind of functions of many arguments. Okay. And the point is that this so if the composite means this composite also belongs to F. I mean, that's implicit in the wording, but what we're saying is if we have some functions in F, we impose them, the composite function is also in F. I made one fussy mistake if one's being fussy, I made one mistake in what I've written. Can somebody spot it?
Shouldn't this be L instead of K?
Yeah, that's not the fussy mistake. That's not the fussy mistake. That's just that was an accidental mistake.
It's not equal.
It's not clear equality. Indeed. So these are a partial functions. We talk about the composition of partial functions. This should again be the following. Just to say, for those of you like category, I occasionally make remarks about category theory. There are notions of so category theory have morphisms and they compose. But here we've got sort of it's awkward to define a category from this data in a sense because of the varying arguments, but there's something called a multi-category. There are actually several different notions of multi-category, but anyway, this is basically saying that we have multi-category here because we have the multi-composition. So the primitive recursive functions for a multi-category. I mean, this is just a side remark for people interested in side remarks. Multi-category. The last condition, maybe I'll put it on this board here so all the conditions are close to each other. Or no, grammatically, no. The last condition is the one that gives the primitive recursive functions their name, and that is that the primitive recursive functions need to be closed under something called primitive recursion. Condition 3, primitive recursion. This is a little bit more complicated to formulate, but it's not a very difficult concept. So primitive recursion says if we have if we have two functions of certain givenarities that belong to the class F. So F is a variable of some arity K. Okay, say. And G needs to have two more arguments than F. So G is a function with K plus 2 arguments. In F, with the family F we're defining, then so is a function that I'm going to call capital R of Fg, where Rfg is a partial function with K plus 1 arguments. And it's defined by the following two clauses, which is that we apply Rfg, so we need to give it K plus 1 argument, so we'll call its arguments x1 through to xk. And if the last argument is 0, then what we get is f applied to x1 through to xk. So it's going to be a function defined by primitive recursion, where recursion is a form of recursion in the computer science sense of recursion. So the function is going to be defined in terms of itself, and this is going to be the base case in the recursion. So in the base case in the recursion, when the number on the right is 0, we use the function f. So f, the point of f is to give us a base case. Of course, f is a priori a partial function. So once again, that should really be a clean quality. And so then we're going to, that's the base case, and then we need the non-base case of the recursion, step case, if you like. So that's what we do if we give, so if we have a, let's stay with what I've got in the notes. So use an x here for some reason. So x plus 1. So in the case we get x plus 1, we're going to define by recursion. So we're going to use the recursively defined function on a smaller value x. And the g is just a way of kind of doing something with that. So we apply g to our arguments x1 through to xk, which are always there for us. We've got two more arguments. The second argument is x, and we've got x plus 1 here. The second argument is allowed to be x, well, is x. So it's 1 less than what we started with, so that gives us that number, which is convenient sometimes. And the third argument is the recursive call, and the recursive call is rf is the function rfg applied to x1 through to xk on the value x, which is 1 smaller than we started with. So we have here rfg of x1 through to xk and x. Okay. And that's it. So the primitive recursive function is the smallest class of partial functions, closed, containing basic functions, containing all composites of basic functions, and containing everything we can get by primitive recursion. Of course, once we get functions from primitive recursion, we can then compose those. So it's all sort of big closure conditions. You can also view it as a kind of way of building up little programs, if you like. Where here we're building up a program in some sort of functional language, where here we're defining programs by composition, and here if we were writing them in a, we're getting certain programs in a functional language, and here we would be simply defining the function using recursion. Okay. And so I will write it down, but I'm going to rub it up again almost immediately. There's a simple fact about the primitive recursive functions, which we're talking about partial functions, but all these basic functions are total. If f and g1 to gk are total, then the composite is of course total. And it's not hard to see that the function that if we've got f and g, and they're both total here, then the function defined by primitive recursion is also total, because the recursion obviously bottoms out at 0 after a finite number of recursive calls. So again, one's defining a total function. So actually, although we've made the definitions for partial functions, there's no way of, we've got the primitive recursive functions are the smallest family of partial functions that satisfy these properties, and there's no way of us getting a partial function. So the proposition is all primitive recursive functions are total. So we could have made the definitions by saying, by just looking at total functions here, and saying the smallest family of total functions, and then we wouldn't have needed, and all functions would be total. Anyway, by assumption, then we wouldn't have needed to use linear equality. So that would be an alternative and more and a clearer way of defining the primitive recursive functions. However, there's a very important reason that I've used partial functions in this definition, and it's not because I want them in this definition, it's because I want to reuse these three clauses later to define the computable, to define the partial recursive functions. And then it's going to be important, then it's going to be vital that the definitions work for partial functions. And we'll come to that when we get to that point. Right, so to end with, we've got like, to end this hour, that is, we've got like 7, well, depending, that clock seems, oh, yeah, no, that clock seems slower than it was last week. Or maybe my watch is faster, I don't know, in which case. Anyway, it doesn't matter, we'll just see when we finish. So I'm going to demonstrate that a few functions are primitive recursive. So we'll start off with, let's get the right one. Right, so the first function I'll call little f1. It's a total function, and it's simply the identity function, and that's primitive recursive. Why is that primitive recursive? Because it's a projection. It's simply the projection from a 1 tuple to the only argument it has. Okay, so that's primitive recursive. The next one I'm going to use G1, which has got 3 arguments. And this is the function that takes x, y, z and returns z plus 1. So why is that primitive recursive?
You can project then everything.
Yeah, we'll project and compose with the successor. Yeah, so we're using projection on the third argument and composition with the successor because that's primitive recursive because G1 is the successor. What did I call the successor? S composed with U3, the third projection. Okay. So now I'm going to define H1. So I can simply define F1 and G1 like that. I'm going to define H1 to be what we get from primitive recursion. We use, but we've got the right arities to apply primitive recursion because this has 2 arguments. The G function has 2 arguments more than the F function. So we can do this. And let's see what function we get. Well, if we apply F1, G1, the primitive recursion of F1, G1, well, so this. So here we have H1, what's its arity? F1 has arity 1, G1 has arity 3. What's the arity of R of F1, G1? 2. Is K is 1, so we get K plus 1 is 2. So we got 2 argument function. Well, we know it's a total function, primitive recursive function, it's a total. So if we apply, well, let's look at what it does. So if we look at what it does on x and 0, so by this, what we get here is f of x, which is, so the f is f1, so we get, this is f1 of x, which is x, that's the identity function. And if we look at R, F1, G1, applied to x and y plus 1, well, then we get, like this, we get G of x y, and the recursive call. So this is G1 of x, y, and the recursive call is R F1 G1. So let's call this H. So I already did. This I don't need to write so much. So this is, so here we go, H1 of x, y. Yeah. So that's what it is. Which is, because, hang on. Yeah, so G1 of H1 xy is of xy, sorry, G1 of these three arguments is the third argument plus 1, so that's H1 of xy plus 1. Okay, so we've defined the function H1 in two arguments that when applied to x and 0 gives x, when applied to x and y plus 1 equals self on x and y plus 1. What's that recursively defining? Which simple mathematical function? Plus addition. So the binary addition function is uniquely specified by these outside equations here. So H1 is the addition function. And well, I could write it down, but the board seems to be conveniently full. So so very, once one's got addition, you can make very similar definitions and use addition to define multiplication, binary multiplication. Once you've got multiplication, you can make very similar definitions and use multiplication to define exponentiation. Once you've done that, you can also define what's it called, iterated exponentiation, things like that. But anyway, this is like the basic first step in getting started with defining functions and showing that they're primitive recursive. And I think, so next week's exercise class is going to be a whole lot of defining functions and showing that primitive recursive. And in fact, primitive recursion, the ingredient is very simple. You've just got a few basic functions, composition, and your only way of really doing something interesting is this primitive recursion, which is a very restricted form of definition by recursion. But in fact, you can define really a lot of mathematical functions this way. Okay. Well, so we'll have a break for 15 minutes, which by the clock on the back wall means we'll start at 13 minutes past 3, but it's 15 minutes from now.
This sounds a lot like some sort of inductive type specification.
Of inductive type specification.
I mean,
yes.
I'm asking if there is something actually.
Absolutely.
Yeah. So
yeah.
At least you want the polynomial factor.
Right. This is a very good question. I'm actually going to put. So the question is this related to inductive types and their recursion principles? I'm going to pause the video. The answer is yes, but I'm not going to put that on the video. Okay. That's a good question in the break, which was, how do you actually prove this from the definition? I'm not going to give the proof, but I'm going to just talk about how the proof works. So the point is, how does it follow formally from the definition when we define this class of primitive recursive functions in this way as the smallest collection of partial functions closed under these three properties, we simply prove, or let's just say verify that the family of all total functions contains the basic functions and satisfies 2 and 3. So it satisfies 1 to 3. And then, since we've defined the primitive recursive functions to be the smallest such family, that means the primitive recursive functions are included in the total functions, therefore every primitive recursive function is total. So since the primitive recursive functions are smallest such category, category on the brain, smallest such collection, family, they're included in the total ones, so every prim rect function is total. So those are the primitive recursive functions. But it's not all the computable partial functions, because there aren't any partial functions. We know that some, one can compute some actual partial functions, like there's the very simple function that just always goes into a loop, because it's not very useful, but anyway, it's at least computable. It's more tricky, but this collection of functions is not even all the total computable functions either. Maybe we'll see that later in the course. It's a very famous total function that has like a 3-line definition in its modern incarnation that's not computable. So that's computable but not primitive recursive, and that's known as the Ackermann function. Not every. Maybe this will be covered a bit in the exercise class next week. I don't want to spend that much time on it. It's a beautiful function, not every primitive, not every total computable function. It's primitive recursive. E.g. the function. So, don't know the Ackermann function. Should look it up. It's got, as I say, it's got a really simple definition. The modern definition, you define it as a 2-argument function, and the way you prove that it's not primitive recursive is you prove that it grows faster than any primitive recursive function. So it grows very, very quickly and grows so fast that you look on the diagonal, you've got Ackermann 1,1 is some very small value, Ackermann 2,2 is not too bad either, but Ackermann 4,4 is so monstrously huge that nobody could ever write it down in the space of the universe or something like that. And it plays an interesting role in some various strange places in mathematics, like if you know about union-find data structures in computer science. So they're kind of almost constant time, but not quite constant time. And the precise bound for why they're not constant time is the inverse of the Ackermann function, which is a kind of very small function because it grows so quickly. Anyway, that's taking us off topic here. Right. Anyway, so those are the primitive recursive functions. There's actually a deep sense in which one cannot capture the computable total functions in this way, not the computable total functions by such a definition without including some partial functions. But that again would take us off topic just to be, we might say, can we add something, like say, let's say we add the appendant function as a basic function, could we then get the computable total functions? But actually, whatever we do, we'll never get, if we stay with total functions, we'll never get all the computable total functions. But when we'll move to the world of partiality, for some miraculous reason, everything is solved very nicely. And all we need to do is add one more clause, and we end up with something which captures all the computable partial functions, so including all the computable total functions. But one's required to have some partial functions, the computable partial functions in that too. So to do that, we're going to define a new class of functions, which is one of main interest today. So this is actually I could have kept functions there. In fact, I could have kept primitive as well. But anyway, it's the partial recursive functions. So partial recursive functions are the smallest collection of partial functions satisfying, well, the same properties. We simply add another one. We simply give a new way of making functions. So we've got basic functions. We can make new functions by composing them. We can make new functions by primitive recursion. We're going to give ourselves one more way of adding new functions to the collection. We're going to, of course, number that one 4. And 4 is going to give us some genuinely partial functions, so functions that are not total. And because of that, then we still want to be closing the functions under composition, the partial functions under composition, and under primitive recursion. So because of that, it was important to make these definitions to say how these means of combining functions, composition and primitive recursion, how they work on partial functions, which is why I included partial functions in the definition in the first place. Having said that, it will actually turn out to be a fact at the end that we can prove that that it's enough to, well, that actually that's less important than it would seem. Yeah, let me not get sidetracked by that now. The important thing to do is to tell us to tell you what condition 4 is. So we've got basic functions. We've got composition. We've got primitive recursion, and 4 is a very interesting little operation on functions. Sort of search operation called minimization. But the rest all stays the same as it did before, minimization. And minimization, I need my notes because otherwise I'll make a mistake. So minimization says, again, we're defining the smallest class F such that something's whole and it's going to be a bigger class because we add this further condition. So if we have a function k plus 1 arguments, that's in the class F, then so is function which we'll call mu of F, Greek letter mu. We use a mu because it's like an n for minimization, I guess that's the reason. So this is a function in k arguments, so we lose one argument. And it's defined by mu of f. We need to give it k arguments. I won't put an equals and then say what have I done wrong. It's clearly equals because it should be partial. We've done enough of that by now. So clearly equal to. So what's it going to be? Well, what we do, we've got a function in k plus 1 arguments. So it's expecting x1 through to xk and the further argument x. So we give this function x1 through to xk, and it's like a root finding function for algebra or something like that. We want to, if this was kind of computing a polynomial or something like this, and we're trying to find the root of it, we look for a value of x such that together with x1 to xk, we get, and that x, the function f gives us a 0 back. And we return the smallest such value if it exists. So we return the smallest n such that f of x1 through to xk, so the k arguments here. So we're looking for, yeah, I've said n for some reason, so let's keep it like that. So we're looking for, yeah, we're saying, does f have a root with these first k parameters, x1 to xk? Let's find it if it does. No, does it have a root? Does it equal 0? If it does, we'll return the smallest such root. Okay? If this exists, so if such n exists, it might not, because maybe f is the function that's, or the constant 1 function, in which case it's not going to have any. So f takes k, f takes k plus 1 arguments, maybe it's the constant 1 function, in which case it's not going to have any root. So we can return the smallest root, if you like, if it exists. And if it doesn't exist, well, this is where we use the fact that we've now got a partial function. This means undefined, otherwise. So if no, in other words, if no such n exists. Now, I've left some space here because this is not quite the end of the story, what I've written here. And there's a reason for that. And let's think how we would try to compute it. With primitive recursion, we kind of compute it by recursion, and eventually we get down to the base case. How would we try to compute this? Well, we want to find the minimization of f on the values of the parameters x1 through to xk. There's an obvious way to do it. We'll test f x1 to xk with 0. If we get to 0, hey, the smallest such number is 0, so we return 0. If we get some other number, well, that's not a root, so we go on and we test f x1 through to xk. If it's 1, then, we test f1 x, we test f on x1 to xk together with 1 as the last argument. If that's 0, well, then that's the smallest root, so we return 1. If not, we carry on, we test it on 2, and we keep on testing until we find a number for which the value is 0. And if we never find such a value, well, the search will go on forever, but that doesn't matter because the functions, we're saying the function's undefined, which is what it will do. Okay, so that's kind of a procedure how to compute it, but there's a problem with that. Can anyone see what the problem is?
Maybe. So
yeah, very good. Now f may be a partial function, and its partiality, when it's undefined, you think of that as a machine computing f might compute forever. So in particular, it might be the case that fx1 through to xk and the value 0 runs forever when we run that. But when we put the value 1 in here, we actually get a 0 back. But we're never going to find that if we start searching at 0, because we'll go into a loop and we'll never actually find out that 0 didn't work to put the right value of 1 in. So actually, there's another condition here which allows us to do it, we return the smallest n such that this equals 0 and also f x1 xk n is defined for all n strictly less than n. Okay, so if it's defined and this is the smallest value for which it is 0, then f applied to smaller values of n is necessarily defined with a natural number value that's different from 0. Right? So really the if such n exists goes here. So the smallest n such that these two conditions hold if such n exists. And undefined otherwise. Okay. And that's it. Those are the partial recursive functions. Maybe we've been good staring at this bits of board for long enough now.
Does this change create a less expressive language, or is the same expressive language just more convenient for the interpretation? That's it calls
More expressive than what?
the one without the less expressive one without the additional.
We have more functions than we had before. Because we're giving ourselves a new way of putting new functions in the class.
I think at the end.
This and condition is more restrictive than we had before because
Yes, but the expressiveness is the same. I mean, in the abstract.
well, if I put the definition in as I put it first before I put this line, it would be incorrect. We would get some functions in the class. We would get some partial functions in the class which are not computable.
And couldn't you
Because
just
we wouldn't have any algorithm of compute for computing.
couldn't you just run first for 0 and then put 0 in one step and then
So run some. Okay, so yeah, so you could try to get around this by running these tests in parallel. But then the problem is, suppose you run them in parallel and you get back it's 0 to 100, but some of the smaller ones are still running. You don't know that 100 is the smallest value, and there's actually no way of solving that. And you can prove if you change the definition, but if you have that original definition, you can prove that some of the partial functions you get are not computable. So, I mean, there's no obvious way of computing it, and actually you can prove that you can't in general compute. So this is the correct definition. Yeah, okay, it's a good question. So, so maybe this is a very small little thing, but just to show that we can indeed, let's also take this one off. Just to show that we definitely go beyond the primitive recursive functions with this. So we had before that we had the addition function was primitive recursive. So remember h1 xy x plus y is primitive recursive. And if we consider u of h1 applied to x, what's this going to be? Well, if we apply it to 0, then it's going to find the smallest y such that x plus y equals 0 and everything else is defined. So this is 0 if x equals 0. But if x is greater than 0, then we're going to be searching for the smallest y such that x plus y equals 0. Y is looking through the natural numbers and x is greater than 0. And of course, you can't get the for all y, x plus y, because x is greater than 0, x plus y will be greater than 0, but it's undefined if x is greater than 0. But just a simple example that one really gets partiality here. I mean, again, one could consider lots of other examples like this, and somehow the power of programming with primitive recursive and partial recursive functions is going to be part of the exercise class next week. But for our purposes, what we're going to look at now is a theorem, which is the main goal today and why we've defined this, and that is that the partial recursive functions coincide with the computable partial function. So every computable partial function is partial recursive, and vice versa. Computable partial functions. I think it's a really quite stunning result because, you know, what goes into the definition of partial recursive functions is so far removed from thinking about the Turing machines. It's really thinking about what the notion of algorithm is, what the notion of being able to explain some process of computation with finite amount of information and have finite configurations evolving according to precise rules and this kind of thing. And here we've really got just a few closure conditions on a collection of partial functions, and it's amazing that you get the same class of functions. This was Turing that proved this. So we're proving that two classes coincide, so we're going to prove two inclusions. So we'll divide it as proposition A and proposition B.
Sorry, could you maybe adjust the camera?
Oh, sorry, did I forget to move the? Thank you. It's nice to have someone on Zoom. Oh, the camera doesn't want to move. Hang on, maybe I'm pointing it the wrong way. No, I'm not. Come on. All right. Bit of encouragement did the trick. Right. So proposition A is which way around we're going to do it. Every partial rec function is computable. Proposition B is the converse. Every computable partial function is partially recursive. Now, proposition A is not really surprising because we've got some basic functions, we can see they're computable. If we've got computable functions, we know we can close them under composition. Primitive recursion, as I said, you know, it's basically a recursive algorithm in there. And we already discussed with minimization, we discussed the algorithmic aspects because that That was why we made the definition in this way, so that we had an algorithm that would actually compute, we could use a search algorithm to compute the function. So it's basically obvious using our informal notion of algorithm, or the fact that we could quite easily translate this into some programming language. However, at this stage in the course, we only have one definition of computability up to now, which is the notion of Turing machine. So we should really show that these are computable according to computability by a Turing machine. And this, together with what's going to happen in 2 weeks' time when you give your presentations, the whole point of this is we're going to see lots of different definitions of this class of partial computable functions using different machine models. This is, today we've got the most mathematical definition, namely the partial recursive functions. And we're going to see that they all coincide, and somehow, no matter what we do, whatever approach we take to defining computability, then we always seem to get the same class of things. And once we get comfortable with that, we'll be much more comfortable with, we can use our informal notion of algorithm to say whether something is computable. This other direction, for the moment, so we need to show that if we've got a computable partial function, that's a function that we have a Turing machine for, then we can convert that into a function that's partially recursive. That looks pretty far out at the moment. I mean, maybe it doesn't reach some of you, but this is going to be where most of the work is required, and we're going to do that one in the third hour. We're going to spend the rest of this hour, I've got 20 minutes left for showing the proposition there, so showing that if we have a partial recursive function, showing that the partial recursive functions are computable according to the definition we have with Turing machines. Okay. Actually, let's see how much of the board do we see. That's okay. Good. I'm going to take the minimization part off. Right. So to do this, we want to convert partial recursive functions into Turing machines that essentially compute them according to our intuitive way of computing them. To do things nicely, it's convenient to very slightly redefine what it means to be a computable partial function. So last week, I gave two definitions, one using multi-tape Turing machines and another using representations, and I said they're equivalent. I'm going to give another version using, again, multi-tape Turing machines, but with a slight difference, which we're going to see where that's useful in the proof. It's a very small difference. And so let me just state the proposition. So a partial function f k arguments is computable if and only if. So last time at the beginning of the lecture last week, we defined computability using a k-tape Turing machine. It's going to be convenient to have use instead a k+1 tape Turing machine. Such that all x1 to xk numbers and words w1, wk, binary words representing x1 to xk. So remember we're using the binary representation of numbers, canonical representation from last week. If we run the Turing machine with W1, WK on the first A tapes. And machine halts, which means terminates in the halt state. Halts if and only if f is defined on x1 to xk. And in that case, so in which case it holds with a representation of the required value x1, f of x1 to xk on the k plus 1 tape. And so I'm using one extra tape from last week, but the other thing I'm going to require is that we stay in it holds with W1 to WK still on the first K tape. So it hasn't changed what's on the first K tape. You still have that data around W1 to WK on tapes 1 to K. Now it's really easy by this stage to see that that's equivalent to what we had last week, that if you had a Turing machine that puts the result, wipes the other tapes and puts the result on the first tape, then that's the same thing as, it's easy to translate that into one that keeps the inputs and works on the K plus 1 tape as well. Easy to go between the two definitions. Just this is a bit more convenient for proving proposition A. So how are we going to prove proposition A? So what we do is we show that, okay, so proof of proposition A. It's similar to the proof we had at the start of this hour, which is we're going to show that the partial computable functions satisfy 1 to 4. The collection of partial computable functions satisfy 1 to 4. Contain the basic functions, closed under composition, closed under primitive recursion, closed under minimization. Therefore, the smallest family satisfying 1 to 4 is contained in the family of partial computable functions, namely every partial computable function is computable. Every partial recursive function is computable. Sorry, I said partial computable a few times when I meant partial recursive. Then you can go to the video and hopefully get a picture of the correct ones. Anyway, we're proving. Let's write on the board. We show that the family of computable partial functions satisfied 1 to 4. Then since the partial recursive functions are the smallest such, since the partial rec functions are smallest such class family, every partial rec function is useful. Okay, so then we have to do the various things. We need to prove the basic functions are computable. That's easy. Prove that the computable functions are closed under composition. That's pretty easy, and we've done similar things already. So the two main jobs we have to do are show that the computable partial functions are closed under primitive recursion, and that the computable partial functions are closed under minimization. Since I've rubbed minimization off the board, let's prove that they're closed under but they're closed under primitive recursion. So I'll rub this definition of computability off, whether we're going to use it. And I should say this proof is actually not in the lecture notes, in the LaTeX lecture notes, so you need to take notes on this if you want to be able to, including this part, but that part's easy now. Okay, so we want to show that. I'm just wondering whether there's going to be enough space. Maybe we can also rub this part off in a moment. So we're going to show closure, and we show that the partial recursive functions are closed under primitive recursion. Primitive prim.rec. So by that I mean they satisfy 3. So suppose we have a k argument partial computable function and a k plus 2 argument partial computable function. We need to show that the primitive recursive defined function is computable. So we're computing now the definition I just rubbed off the board. We compute a k argument function with a k plus 1 tape Turing machine. So we have by assumption a k plus 1 tape TM computing F and the k plus 3 tape TM computing G, where F has k arguments and G has k plus 2 arguments. We're going to define a k plus 4 tape computable function, Turing machine, to compute this k plus 1 argument function. Of course, that's using 2 tapes too much, but then we can use the kind of things we did in lecture 1 or 2, lecture 2, when we were translating between multi-tape machines to reduce it to the right number of tapes, for k plus 2 tape machine. And it's convenient to use the additional tapes. So we're going to define a k plus 4 tape machine computing RFG. And basically, the idea is we're going to in the Turing machine world, we're going to write a program to compute iteratively this function that's defined by primitive recursion. We're not going to do it explicitly via recursion, because if you're implementing recursion, you need to use stacks, and we're going to sort of unfold it to an iterative approach as well, because that's easier to do instead, because that's easier to do on the Turing machine. So we've got k plus 4 tapes. What are they going to be? We've got just write the tapes as horizontal lines. So we don't have to write too much. So these are going to be the arguments x1 to xk. That we're going to give to the primitive recursive functions. We actually have an additional argument, and that's going to be on the k plus 1 tape. Here we have the argument xk plus 1. On the k plus 2 tape, we're going to put a counter, which is going to start off at 0. And this counter is going to count from 0 up to xk plus 1. And on the k plus 3 tape, we're going to have the result of RFG on the current iteration. And on the k plus 4 tape, we're going to have the result being computed. Okay. And we simply now need to define a Turing machine that's going to do the right thing on these, with these k plus 4 tapes. So we need to basically give a program for computing the primitive recursively defined function that we want to compute. To define that explicitly as a Turing machine will be incredibly tedious. So as always, we don't explicitly define it as a Turing machine. We'll give like a high-level description of how the Turing machine is going to work. So the TM proceeds as follows. So firstly, so it starts off with the arguments x1 to xk and xk plus 1 on its tape, which these are the arguments we're giving the RFG function, the k plus 1 arguments. And it starts off by initializing the k plus 2 type, the k plus 2 tape. So it's a counter initially 0, so initialize k plus 2 tape to 0. That's step 1. Okay, so what we want to do is we'll want to compute. If we unfold this, and we've got whatever our k plus 1th argument x is, and if it's not 0, it is g of something, where the last argument is again g of something all the way down, and if you unfold this all the way, eventually you get an f of x1 to xk in there. So that's kind of starting from the top as you would compute things recursively. Instead, we can start from the bottom and compute firstly RFG of x1 to xk of 0, and then use that value to compute the value for 1, and so on. So we're going to do that. So we're first going to compute RFK, going to compute the function with, sorry, not RFK, RFG of 0, where the k plus 1's argument 0, and then the value is f of x1 to xk. So we use, so we'll call this m sub f and m sub g, the two Turing machines. We use mf to compute f of x1 to xk, and we write the result on tape k plus 4 on tape k plus 4, which is where we want the final result to be. Is if our case argument was 0, this is the final result. So step 3, we compare the numbers on tapes k plus 1 and k plus 2, so our counter and the argument, and if they're the same, which at the beginning means if our last argument is 0, so if the numbers on tapes k plus 4 and k plus 3, so when I write in brackets, I mean the tapes are equal, then hold. So if we started off with 0 on the k plus 1's tape, that's our k plus 1th argument. We put the 0 there, the numbers agree, we halt, and indeed we have the correct value f of x1 to xk on tape k plus 4, which is what we wanted. Otherwise, if they're not equal, we're trying to count up towards this value and eventually get to it, so we need to keep going. So if they're not equal, well, we copy the result that we had for this iteration, we copy it to the k plus 3 tape. So we got it for the next round of computation. So we copy the k plus 4 tape to the k plus 3 tape. And then we're in a position that we can apply a function that's computing G to compute. We apply it on tapes. So it's a K plus 3 tape machine. We apply it on tapes 1 to K, K plus 2. So this doesn't mean 1 minus K, it means 1, 2K. Let me write it. 1 dot 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 K, K plus 2, K plus 3, and we write the result on K plus 4. But the point is we're using, as the arguments, we're using 1 is the arguments of G. So G needs to take x1 to xk, those are on 1 to k. It needs to take the previous value of the that we're computing it on, and that's the current value of the counter, because we haven't incremented the counter yet. And it needs to take the recursive call, and the recursive call is on tape k plus 3, because we copied the previous result from k plus 4 to tape k plus 3. And then it writes the result onto k plus 4, because that is where we want the result to be. Okay. Now we increment the counter. So increment, in other words, add 1, take k plus 2. And then we go to step 3. Go back to step 3. And that does the trick. The only thing is it's a k plus 4 tape machine, so we need to reduce it to a k plus 2 tape machine with the result on tape k plus 2. But as I said, that's easily done by kinds of things we did in lecture 2. Right, so it's now 1 minute past 4 by the clock on the back wall, so we'll start at 16 minutes past by the clock on the back wall. Are there any questions? Yeah. Right. Okay, so I didn't rub off these 2 boards because it turned out there was quite a bad mistake in what I wrote, and since this isn't in the notes, it's important to say this. So we're computing the primitive recursively defined function. And the idea was you give it its k plus 1 arguments on the k plus 1 tapes, and you use this counter and this kind of record of the current last result on the k plus 2 and k plus 3 tapes, and eventually you put your result on the k plus 4 tape. And you do it from the bottom up, so starting with the 0 case and then the 1 case all the way until you get to the k plus 1 case. So the point of this counter is to count up to the number on the case that you start with on the k plus 1 tape. So here I don't remember what I had, but something like k plus 3 and k plus 4. And that was nonsense. This is supposed to be the counter is counting up to the k plus 1 tape. If these 2 are equal, then we finish. And then we opt.
Have you said it correctly, though, because I have.
Oh, okay. I might have said it correctly, but I certainly wrote it to be correctly. Right. So now we can erase this, and the remaining thing to do is to prove proposition B, which is that every computable partial function is partial recursive. And yeah, it looks quite remarkable when you first see it. But if it's going to be true, there's an obvious way to prove it, and there's really only one obvious way to prove it, which is if we've got a computable partial function, we can compute it by a Turing machine. We want to show that that's partial recursive. So we want to what we need to show somehow is that we can simulate Turing machines using partial recursive functions. And then if we can do that, we then, you've got something we can compute with the Turing machine, we code it up so that the partial recursive functions simulate the Turing machine, and then we package that inside something that initializes the Turing machine correctly and extracts the right result at the end. And that's what we're going to do. And in order to do that, we want to encode the Turing machines up using partial recursive functions which act on natural numbers. So the first thing we're going to have to do is encode everything to do with Turing machines as numbers. Now that's a relatively straightforward exercise, but nonetheless, this is going to be something that's going to be very useful for us throughout the course, encoding all kinds of mathematical things as numbers. So we're going to spend a bit of time doing that. So
these encodings similar to Gödel encodings for that?
Yes, indeed. Have you done Gödel encodings?
No, but I know we're gonna do them in logic.
Yeah, we will do them in logic.
So are these the same encodings for some basics?
Well, we're encoding different things.
Yeah.
In logic, you're encoding formulas of logic. In here, we're encoding Turing machines, but still you need the same basic ingredients. You need to be able to encode tuples and sequences and things like this as numbers. So I'm just going to, maybe some of you have seen this kind of thing before, but I'm just going to give you one way of doing this. So we want to encode, we're going to encode pairs, ordered pairs, using n. So the easy way to do this is to give a bijection but from n times n to n that one wants to be as simple as possible and in fact computable and even more. So the easiest one I think is this function p(x) of y is a half times x plus y times x plus y plus 1 plus x. And this works like this, that if we have x here and y here, 0, 1, 2, 0, 1, 2, and so on, then it goes like this, it goes down the diagonal, so it's 0, 1, 2, 3, 4, 5, going down these diagonals. 6, 7, 8, 9, etc. And what's important for our purposes is the p is a function from pairs of numbers to the natural numbers is a bijection. More importantly, that is important, but also important, P is in fact primitive recursive. And you will be able to exercise, try and show this for yourself, but you'll certainly be able to do this very easily after next week's exercise class. And then the projection functions which are Q1 and Q2, which are just functions on natural numbers here. But the point is that they represent the projections in that if we encode a pair and we apply Q1 to it, we get X back, and Q2 of P XY is Y back. These are also primitive recursive. And again, think about that. But it will be easy to show after next week's exercise class. As a matter of fact, I don't think there's any sort of simple algebraic expression for Q1 and Q2 in this case. So if somebody knows one, I'd be very interested. I'd be very interested to see it. It doesn't matter because it's primitive recursive, and that's what we're going to care about. Okay, so that's how we define pairs. And once you've defined pairs, we can define triples, because a triple is like a pair where the first argument is a pair, and so on. So triples are easy, but we can use that kind of code for coding up tuples of any fixed length. But something that's really important in encoding Turing machines is words, where words don't have a fixed length in advance. And words then are represented as sequences, or finite sequences. So we're also going to give an encoding of finite sequences. So to encode finite sequences, we're going to use a function which I'll use this kind of top left and right corners, and I'll put the argument here. The dot means that's where the argument goes. So this is going to be, so encoding of pairs is a binary function, so we're going from n squared to n. Encoding of sequences maps every sequence over natural numbers to natural numbers. And again, I want to do this in such a way that we get to bijection. I mean, actually, it's only really important to get an injection that has a decidable image, primitive recursive image, in a sense. But anyway, it's easy enough to give a bijection. So just to say, actually, if one's giving, there are many ways of encoding sequences. A very popular one is you take a sequence of numbers and you use a product of powers of primes to kind of go to the sequence. But if you do that, it's harder to engineer getting a bijection, although it can be done. But instead, the way we're going to do it is we have a sequence. So remember, we have a word and numbers, and I'm going to do the counting from 0. So a word of length k here, n0 to n k minus 1. I like this encoding, where we define this to be the encoding of a sequence is defined to be 2 to the n0 plus 2 to the n0 plus n1 plus 1 plus 2 to the n0 plus n1 plus n2 plus 2 plus, then the last term is 2 to the n0 plus n1 plus all the way up to plus nk minus 1. We're adding all these, all the elements. And then, I hope I've got it right, we add k minus 1 at the end. Okay, and there's an explicit sigma form for this in the latex notes that I won't write down. But the idea is this, that we're encoding it as a number, and the number is a binary word, so like something like that. This is n0, the number of zeros here. This is n1. This is n2. This is n3. This is n4. So this is the encoding of the sequence 1, because it's 1, 0, 3, 0, 5, 2. So this is 1, 0. Sorry, 1, 3, 0, 5, 2. 1, 3, 0, 5, 2. Okay. And once again, we have this function from words to natural numbers is a bijection. The empty sequence gets mapped to 0.
Or we could think of these as binary numbers. And like how would
sorry.
3 be mapped back?
Sorry?
Like, what would be the inverse of 3?
Oh, no, sorry. So it's yeah. So it's yeah. This as a binary, the number given by this in binary. Yeah. The number written in binary. Sorry. Yeah. There's a bijection. We can't say it's primitive recursive because it's not of the form of a primitive recursive function. The primitive recursive functions need a fixed, they're on the natural numbers for some fixed k. We don't have a fixed k here. It is computable with respect to a natural representation of n stars, any natural representation of n stars. So it is computable, but that's not really going to be important for us. What is going to be important is that the following functions are primitive recursive. So here we have the projection functions, which are how we extract data from a pair, primitive recursive. And we also want the how we extract data from a word functions to be primitive recursive. So these are the functions using void. So the functions sigma, which takes the encoding of a word over numbers and an index I, and I do, thank you. I've actually got this half of the board on, but yeah. Fortuitously. So this function is the function that takes the encoding of a word and an index and returns the character with index I in the word. So in other words, we'll return WI if I is less. So remember, we count through the characters of the word W from 0 up to I minus 1. Those are the indices. Sorry. So if I is less than W, only actually what we really want of this function is we want to get a value of we want to be able to get the characters out. We also want to know if our index is too big. So to do that, we'll give ourselves 0 if the index is out of bounds. So if I is greater than or equal to length W. And to avoid getting conflicting information, we'll add 1 to the, so when we get an element of a character from the number from the sequence, we add 1 to it to make sure we don't conflict it with 0. Once we've got that, we know we've got a character in the word, and then we can subtract 1 if we want to get the character. Okay, and the other function is L, which stands for length. So sigma stands for select. Sigma select. And L stands for length. And L, of course, we give it the numerical encoding of the word W, it gives us the length W. And these functions are again primitive recursive. Right, so now we're going to use this kind of way of encoding data to, we want to show that every computable partial function is partially recursive. So what we're going to do is we'll start off with a Turing machine that computes the computable partial function, and we'll use this kind of encoding of things with numbers in order to encode the Turing machine up, and then we'll be able to simulate the Turing machine using partial recursive functions. So now to prove proposition B, that was that every Turing machine, every computable partial function is partial recursive. Let's suppose we have a Turing machine. Suppose f from n to the k to n is computable. Suppose it's computable and moreover it's computed by Turing machine n. And for this, it's convenient to go back to the original definition of computable partial function that we had last week, where we've got the partial functions computing on as given by Turing machine on using the mapping the representation of k tuples of natural numbers to the representation of natural numbers. And it can be, by what we did in the first 2 weeks, a single take Turing machine. So n is a, because we want to encode the workings of a Turing machine, it's better to have the simplest form of Turing machine possible. So n is a single take Turing machine computing f by representations. That's the last week's lecture. So suppose n has take alphabet gamma. Okay, so just to see that you're concentrating, what do we know about the tape alphabet? Do we know anything at all about it? It has blanking, very good. We've known that since lecture 1. Anything we know about it since lecture 3, since last week's lecture? Well, n could be a very complicated machine, because it's just some assumed machine for computing m, but it has to compute with the representations of k tuples of natural numbers and natural numbers. So we know that it. So let me see. Yep, I've got blank here as well. So we know that it contains blank, and it contains 0 and 1 because it has to have binary numbers, and it contains comma, which is the. Okay, that's everything we know about that. And states that Q. We don't know anything about the. Oh, we know that the state set contains fonts and start. So what we want to do is we're going to encode configurations of this Turing machine using numbers. So configuration is a tape configuration. So you've got some finite amount of non-blank data written on the tape, together with a head position and a state. All right. So to encode that, we're going to choose, these are finite sets, so it's easy to choose this. We'll choose injective functions, and they're automatically computable. Well, they're finite functions because they're defined on the finite set. R from which stands for representation, So this is mapping the tape alphabet to odd numbers, and S standing for state, mapping the state set to even numbers. And the point of separating out the alphabet in the state set is just so you can tell, if you've got a number, you can tell which kind of thing it's encoding. Okay.
These are very much non-circular. So
They're very much not, because these are finite sets, and they're injective functions, so they're very much not selective.
for a given number,
Yeah.
we have probability 0 that actually representing some lifetime machine. Either
Yes,
yeah,
absolutely. Very depends what probability distribution you're using to choose an arbitrary number, which is an interesting question in itself. But yeah. Anyway, then we've got finite things, so we only need finitely many numbers to record them. Anyway, once we've done that, how are we going to represent a tape configuration? So there's something in the notes here. I'm going to try and do it pictorially instead. It's done in, so as I said to before, the notes are not very visual. So try to do things in the lectures with more visually. So suppose we've got a tape configuration and we've got A1, well, let's say A0, A1, A, K minus 1. And what's important, these are obviously elements of the tape alphabet. They can be blank, but what's important is we've identified some portion of the tape so that contains all the non-blank, contains everything that's non-blank. And let's have an AI in here as well, somewhere between 0 and that, because I want that because we've got the head position pointing somewhere, and we've got some state Q. And what we represent this configuration. So let's call it C because it's configuration. Again, I always like to use these corner brackets for encodings. So this is the encoding of the configuration. Is defined to be. So what we do, there's a nice trick for doing this, which is we're going to write the sequence of tape characters as a sequence of numbers using the R function. So we have R A0. There's the sequence whose first number is RA0, whose second number is RA1. And we're going to put the tape head position together with the state information in the same point. We're going to use the state information to tell us where the head is. I will do this as far as RA of I minus 1. We'll then put in S of Q into the sequence. So that's saying the head is underneath the next character. Then we go from RA of I all the way up to RA of K minus 1. That's a sequence of numbers, and we want a single number representing the whole thing, so it's the number, so it's whatever number represents that sequence of numbers. Okay. Once we've done that, so things may be appearing to be lumbering very slowly on, but we're doing sort of one encoding after another, but we're basically there now. We've encoded configurations, and that's what we need because the computation of the Turing machine is going to be a sequence of configurations. And we're now going to use the partial recursive functions to code up initializing the Turing machine, performing a sequence of computation steps, and then extracting the result of the Turing machine at the end. And now this is not the kind of proof where one gives every detail. In fact, it's the kind of proof where one gives very few details at all, and one sees that actually it's doable in principle. And I'm just going to now claim that a whole sequence of functions are primitive recursive. And you will appreciate this once again after next week's exercise class. And maybe you will appreciate quite how much work goes into showing well, a point. But for now, I'm just going to state it as a fact. But what's going to be interesting is not why they're primitive recursive now, to say that's for next week's, that's for, you will understand that sort of thing after next week's exercise class, and more what these functions represent in terms of how we're simulating the Turing machine. That's what I want to focus on. So the following are primitive recursive. Now we're in the interesting position that actually modified the notes on this today, and the new notes are online, and someone might be following them, but I got a printout of the old notes, and I thought, well, I know what thought process I went through in modifying them. So I hope I can do the modifications again. So the first one, I'm going to call step, which is a unary function on the natural number, of course, stable because it's primitive recursive. And point of step of x is if we're in a configuration, step of x, so step of x, if x is the coding of a configuration, step of x is going to be the configuration we get to by one step of execution of the Turing machine on starting in that configuration. Okay, so step of x is the encoding of C prime in the case that we start with the configuration where x, if x is the encoding of the configuration C and m takes one step from C to C prime. Okay, so one step of the execution of M to C prime. And I'm going to put 0 otherwise. Okay, so why didn't I add one here? And in order to not have any conflict, for two reasons. Firstly, we never need to use the otherwise case, because we're only going to use it in the case that we start off with the configuration and everything's going to preserve the encoding of the configuration, so we never need to use that. But also, the encoding of the configuration can never be 0 because it has to involve some state, and the state will always be well, the state's an even number, but it's always non-empty. It's always non-empty. Well, it always means you've got a non-empty sequence, so it's not going to be 0. Anyway, good. So once we've got step, we can do run, which is going to be run the Turing machine for a specified number of steps. So run, that's a 2 argument, and we have run configuration given by x for n steps, and that's simply, we can write that simply as the function that iterates the step function n times on x. That's again a primitive recursive function. If you ever have a primitive recursive unary function, the function that iterates into a specified number of times is always a primitive recursive binary function. That's a nice exercise. Then we have the extract function. And the point of the extract function is at the end of the computation, the extract when the Turing machine has to halt in the halt state of the right result on its tape, the extract function is going to read the result and return the number of codes. So the extract function is, this is one of the ones I modified. So extract of x is n, some number n, if x encodes the configuration S of halt, followed by R of W, whereby R of W, this is a word, a binary word, and by R of W, I mean just the sequence R of W0, R of W1, R of W, length of W minus 1. So I just made that sequence of encoding the characters. I'm just using a shorthand for it. And W is a binary representation of N. So that's saying in our canonical representation of natural numbers, W represents A. So this would be X equals the encoding of that configuration, and 0 again otherwise. So what this is doing is it's detecting whether we are in the halting state in the final configuration, which as it's supposed to be the head at the left character of the output word, and the output word is of the form binary word encoding the number n, in which case we return the number n that's encoded by that binary word. That's the extract function. Then we have the halt function, which I'll put a question mark because it's basically a Boolean test. So this is again natural numbers to natural numbers. We were only interested in one bit of value. And actually, we're going to use 0 for the true and 1 for the false, and that's important, as we'll see. I think I said something last week about Daggerin preferring 0 for false and 1 for true. In this case, it's really crucial to use it this way, right? So 0, if x is of the form is a halt configuration as above, or 1 otherwise. And lastly, we need an initialization, which is a function from n to the k to n. And the point of this is we give it the n arguments of the function f that we're using the Turing machine to compute, and it computes the encoding of the initial configuration that we start the Turing machine with. So init of x1 through to xk is well, we always start in the start state, so we need the encoding of the start state, followed by R, so that we want to represent the word that we start on the tape, and that word is, well, let me write it like this, the binary encoding of x1, followed by comma, followed by the binary encoding of x2, followed by comma, followed by so on, all the way up to the binary encoding of xk. So this is So there's a whole lot of data there, but character by character, we use the R function to convert that into a sequence of numbers. We have the encoding of the state in the right position because the head's on the left, and we encode the whole thing. And we encode the whole thing then as a configuration, and that gives us the right starting configuration. And having done that, so all these functions are primitive recursive. having done that, we can now see that the required function f is so then f is partial recursive because f of x1 to xn is there's an equals in the notes here. It should be a clean equals because obviously it's a partial function. Is simply extract the data, extract the final result from what we get by running a certain function. And we need to say how many times we want to run it. Well, how many times we want to run it? So we're going to give two arguments here. The number of times we want to run the function is we apply minimization to a function. Basically, what we're going to do, we're going to search for the smallest number n such that the machine halts when started on the initial configuration. So we apply mu, and I'm going to use a kind of lambda notation here. So we apply mu to the maps to notation to the function that maps n to what we get by so whether or not we halt after we run n, so run comes in again here, after we run run the machine for n steps from the initial configuration given by x1 to xk. Okay. Now I've got 4 closed brackets here in my notes. 1, 2, 3, 4. That's correct. And we run that number of steps on the starting in the initial configuration from x1 to xk. Okay, so the point is, here we've initialized the Turing machine, and we're looking at a function that for any number of steps runs the Turing machine for that number of steps, starting from the initial configuration, and tells us whether or not it's in the halt configuration at that. We're looking for the smallest number at which, with the correct initial configuration, it gets into the halt configuration. If it never gets to the halt configuration, we don't get that number. That doesn't matter. If it does get in, then it's just undefined. It does get into the halt configuration. We say the smallest such number, which is the number of steps after which the Turing machine halts when given the representation of x1 through to xk, which is what we've done with the initialization. Because the Turing machine actually computes f, in that case, we're guaranteed to get a halting state with the correct output information on it. So we simply extract that output information and that's the result of the value that we want. So we're done. And it's a bit fiddly, but I think it's very beautiful how one can basically use these like mathematical ingredients of the primitive recursion and this simple search to be able to simulate Turing machines in this way. Right, okay, so that's it for today. Any questions before we finish?
So primitive recursive function, we're basically encoding for loops with the proper partial function. Kind of encode while loops. We get the
yeah, to a degree, I think primitive recursion is a bit more powerful than for loops. Yeah, because for loops
are the same thing. So
I mean, you've got some recursive power here that's I think
But
I'm not sure how far.
Can you have a branch?
You can branch, yes. Yeah, that's the next exercise graph. Yeah. Good. Other questions? Right, okay, well, you need a break before your exercise class, so see you next week.
Excuse me.
Yeah, so let me just